All right, everyone. Ever wonder how machines actually think? Today we're pulling back the curtain on the basic language they use. Simple on-off decisions that, believe it or not, run some of the most complex systems out there. We're going to get right down to the virtual nuts and bolts, so let's jump right in.
Okay, so think about any automated system, a factory, a traffic light, even a simple robotic arm. At their core, they're constantly asking super simple questions. Is this sensor blocked? Has someone pushed this button? Is it hot enough? All these questions are inputs, and the machine needs a way to take all that information and decide on an output, an action. And that right there is the job of a programmable logic controller, or a PLC. It's basically the brain of the whole operation.
So here's what we've got on tap for this explainer. We'll kick things off with what logic gates even are inside a PLC. Then we'll tackle the basic trio, AND, OR, and NOT. After that, we'll look at the universal gates, NAND and NOR, and then the exclusive ones, XOR and XNOR. And to wrap it all up, we'll connect the dots and see how these simple little things build, well, pretty much all of modern automation.
All right, so if a PLC is the brain, it has to have a language to think in, right? Well, for PLCs, that language is called ladder logic. And the basic words of that language, those are digital logic gates. Just think of them as the fundamental rules, the simplest decision makers that when you string them together can create some incredibly smart systems.
When you look at ladder logic, you're really just seeing a few key symbols. You've got contacts, which are your inputs. They're just like switches. A normally open one is off until you tell it to turn on. A normally closed one is the opposite. It's on by default. And then you have the coil. That's your output. That's the thing that happens, like a motor spinning up or a light switching on.
Okay, let's get into it. We're starting with the big three, the absolute foundation of all digital logic. If you get these, you've pretty much cracked the code.
First up, we've got the AND gate. And the rule for this one is super strict. The output only turns on if input A and input B are both on. If even one of them is off, nothing happens. It's an all or nothing deal. Every single condition has to be met.
So how does ladder logic show us this rule? Well, take a look. The two inputs, the two contacts, are placed one right after the other in a single line. We call this a series connection.
And here's why that's so clever. For the power to get to the output, it has to flow through that first switch and then through the second one. If either of those switches is open, the path is broken. No power, no output. It's a perfect visual for the AND rule. A and B have to be true for that output to fire.
All right, next up is the OR gate. And this one's a lot more laid back than the AND gate. With an OR gate, the output will turn on if input A is on, or if input B is on. Heck, it'll even turn on if they're both on. You just need at least one condition to be true to get things going.
And check out how the diagram totally changes for this. Instead of that one single path we saw before, now we have two separate branches running in parallel. The inputs aren't in a single file line anymore. They're giving the electricity different routes to take.
This setup is everything. It means the power can go through the top path if input A is on, or it can zip down the bottom path if input B is on. Either way, it gets to the output. It's just a beautiful, simple way to visualize that OR logic.
Okay, the last one in our basic trio is the NOT gate. Some people call it an inverter. Its job is dead simple. It just flips whatever you give it. So if the input is off, the output is on. And if you turn the input on, the output immediately turns off. It's the opposite day gate.
And the way this works in ladder logic is just brilliant. Instead of that normally open contact we've been using, we use a normally closed one. That little slash through it means that when the input is off, the switch is actually closed, letting power flow through. The moment you activate the input, that switch pops open, breaks the circuit, and turns the output off. A perfect inverse relationship.
All right, moving on to something really cool, the universal gates. Now, why are they called universal? Because you can literally build any other logic gate using only NAND gates or only NOR gates. That makes them these incredibly powerful, versatile building blocks.
The names kind of give the game away here. A NAND gate is just a not AND gate. It does the exact opposite of the AND gate we just saw. So its output is always on unless both inputs are on. And you guessed it, a NOR gate is a not OR gate. Its output is on only when both of its inputs are completely off.
Okay, but here's the really interesting part. Look how the ladder logic gets flipped on its head to make this happen. For a NAND gate, a not AND, you actually use normally closed contacts in parallel. And for a NOR gate, a not OR, you use normally closed contacts in series. It's the total opposite structure of the AND and OR gates, and that's exactly how they get that inverted logic. Pretty neat, right?
Okay, last group of gates. These are the exclusive gates, and they're super useful for one specific job, comparing two things. You use them when you need to know if two inputs are different from each other, or if they're exactly the same.
So this one is the exclusive OR gate, or XOR. I like to think of it as a really picky OR gate. The output is on only if one of the inputs is on, but not both. It's specifically looking for a difference between the two inputs. If they're both off or they're both on, the output stays off. And yeah, you can see the ladder diagram for this one is a bit more involved. What it's really doing is checking two things at the same time. On the top branch, it's asking, is A on and B off? And on the bottom branch, it's asking, is A off and B on?
It's a really clever combination that gives you that perfect one or the other, but not both, result.
And the flip side of the XOR is, you guessed it, the XNOR gate, exclusive NOR. It does the exact opposite. This gate is all about checking for sameness. The output is high only when both inputs are identical. So either they're both on or they're both off. You can think of it as an equality checker.
And once again, the ladder logic is built to create exactly this condition. If you trace the paths, you'll see that the circuit only gets completed when the inputs are both off or when they're both on. It's just a really smart arrangement that works perfectly to check if two things are the same.
Okay, so we've gone through all these individual gates, all these little rules, but so what? Why does any of this actually matter? Well, let's zoom out for a second and see how these tiny little building blocks create, well, everything in the world of automation.
So here's the big takeaway. All that super complex automation you see out there, it's all just made of these simple rules. Think about a safety guard on a big machine. The machine will only run if the guard is closed and the start button is pressed. See? That's just an AND gate. Or what about a conveyor belt that sorts boxes if sensor A or sensor B gets triggered? That's an OR gate. Programmers just stack and combine these simple blocks over and over again to create the incredibly complex logic that runs our modern world.
And that pretty much wraps up our explainer. We've seen how these super simple rules, visualized as contacts and coils in a ladder diagram, become the actual language that machines use to think. It kind of makes you look around, you know? What simple little process in your own life, with its if this, then that logic, is just waiting to be automated? Something to think about. Thanks so much for tuning in.